gallium has two stable isotopes, and the masses of gallium-69, which is 60.11% abundant, and gallium-71, 39.89% abundant, are 68.926 AMU and 70.925 respectively. You know what respectively means? It means we've got two masses here and two atoms here. So respectively means the first of these masses goes with the first atom mentioned, and then the second one of these masses goes with the second atom mentioned. So don't let that term throw you off. So that's what respectively means. Anyway, calculate the average atomic mass of gallium. So to do this, we're going to want to take the mass of the first isotope, multiply it by its percentage expressed as a decimal, and then we'll take the mass of the second isotope, multiply it by its percent abundance expressed as a decimal, and we'll add the two of them together. So we will start with gallium-69. So what's its mass? It's the first one here, so respectively, we're going to use the first mass. It is 68.926. And now we want to multiply this by gallium-69's percent abundance, but expressed as a decimal. So we'll be moving the decimal place 2 spots to the left, times 0.6011. That's the first part. Now we're going to want to do the same thing for gallium-71. So its mass is the second one here, 70.925. And we multiply it by its percent abundance as expressed as a decimal. Move this place 2 to the left, so we get 0.3989. Multiply both of these together and then add them up, and what you're going to get is 69.72 AMU for the average atomic mass of gallium. Now, if you wanted to just check your work, you could look gallium up on the periodic table. Here's what it would look like, and underneath the element name is the average atomic mass, which matches what we just calculated. Now, very quickly, check this out. We have two isotopes of gallium. One weighs about 69, the other weighs about 71, and the mass is closer to 69 than it is to 71. And that makes sense because there is more gallium-69, 60%, as compared to gallium-71, which is only about 40% abundant. So it makes sense that our weighted average should be closer to this one that's more abundant than to this one, which we don't have as much of. Rubidium has two isotopes, rubidium-85 with an atomic mass of 84.911 AMU, and rubidium-87 with an atomic mass of 86.909 AMU. The atomic weight of rubidium reported on the periodic table is 85.47. And in this question, when they say atomic weight, they mean atomic mass, relative atomic mass. Any of these terms you can use interchangeably. Based on this information, which of the isotopes of rubidium is more abundant? And we're talking about, is it rubidium-85 or is it rubidium-87? And how do you know which one is more abundant? This is a thought question. We don't really have to do any calculation. And it revolves around the idea of relative atomic mass, atomic weight. So now how does this relate to these two isotopes? Well, we have rubidium-85, which weighs pretty close to 85 AMU. And then we have rubidium-87 that weighs pretty close to 87 AMU. So for these two things, the regular average, if we had the exact same amount of both, would be right in the middle. It would be 86 AMU. But instead, we can tell from here and from the periodic table that the atomic mass of rubidium, the weighted average, isn't 86, it is 85.47 AMU. This means that it's closer to the mass of rubidium-85. It's not in the middle, and it's not close to 87. So that means that the weighted average is telling us that we have more rubidium-85 because this weighted average number is closer to this. So there's more of this that's pulling the weighted average number down. So rubidium-85 is more abundant because the atomic mass weighted average is closer to that than it is to this. Magnesium has 3 stable isotopes. Calculate its average atomic mass using the information in the chart below. We've already done this with 2 isotopes, but you can do it with as many isotopes as you need. It's the same process throughout. So let's start with magnesium-24. We're going to want to take its mass, which is 23.985, and multiply it by its abundance expressed as a decimal, 0.7899. That was magnesium-24. Now we're going to go on to magnesium-25, take its mass, 24.986, multiply that by its abundance as a decimal, so 0.1000, okay? And then finally, magnesium-26, 25.983 times 0.1101. I fit it all on one line. So we're going to do this math, and we're going to end up with 24.31 AMU is the average atomic mass, and you can check yourself by looking it up on the periodic table, and you find that the reported atomic mass is the same as what we calculated here. Here we're going to do some problems where we already know what the atomic mass of an element is, and we have to figure out what the percent abundance of various isotopes of that element are. Here's a typical question. There are 2 stable isotopes of chlorine, chlorine-35 and chlorine-37. I put this in visual form for you. So here are the 2 atoms, and here are the masses, 34.97 AMU and 36.97 AMU of these 2 isotopes. If the relative atomic mass of chlorine is 35.45 AMU, so like that's what it is for the element itself, what is the abundance of each of these isotopes? So in other words, what we're solving for is what's the percent abundance of this one, and what's the percent abundance of this one? They're both unknowns right now. So how are we going to go about solving the problem? Since these are unknowns, the first thing let's do is assign some variables to. Chlorine-35. just for the sake of it, let's call that X. The percent abundance of it will be X. What about chlorine-37? Well, we could say that it's Y, but that would be a pain because then we'd have two variables to solve for, X and Y. Now, they make things much more difficult. What we really want to be able to do is express chlorine-37's abundance using X in some way. Let me show you how we're going to do it. I want to show you just some random possible abundance values for these two isotopes, just so you can see a pattern here, and then we'll figure out how to solve for it, okay? Let's say just randomly that there could be, I don't know, 60% chlorine-35 and 40% chlorine-36, or if we express these as decimals, it would be 0.6 and 0.4, or there could be 25% chlorine-35 and 75% chlorine-37. They're the decimals, 0.25 and 0.25 and 0.75, or we can have 80% chlorine-35, 20% chlorine-37. Again, I'm just making these up, and we have 0.8 and 0.2. Do you see the pattern going on here? Because we only have two possible isotopes for this problem, when we add the two of them together, they always have to come out to 100%. Or, if we're expressing our abundances in decimals here, when we add the two abundances up, they have to come out to 1. We can use this to come up with an expression for chlorine-37. Here's the first thing that we've noticed. Chlorine-35 plus chlorine-37, when they're expressed as decimals, add them together, you'll always get 1. So we can just rearrange this equation here to solve for chlorine-37, and then we get chlorine-37 equals 1 minus the amount of chlorine-35 that we have. So, chlorine-37 here is going to be 1 minus the amount of chlorine-35, which we are saying is X. So here are two variables, X, the amount of chlorine-35, and 1 minus X for the amount of chlorine-37. Add the two amounts together and we're going to get 100%, or we're going to get 1 if we're expressing them as decimals. So now we're ready to write an equation that sets these variables up. What's it going to look like? In order to do this, let's take a look at a related equation that we'd write when we want to find out the atomic mass and we already know the abundances of the isotopes we're starting with, okay? Here I got boron 10, I take its weight, 10 AMU, and I multiply it by its abundance as expressed as a decimal, and I do the same thing for boron 11, multiply it by its abundance expressed as a decimal. So I'm going to do that here, except we just already know the atomic mass. So let's start out with chlorine-35. Okay, I'll start out with its mass, just like we have the mass of boron 10 here. So the mass of chlorine-35 is 34.97 AMU. Down here, we multiply this by 0.2 because we know the percent, but for chlorine-35, it's just going to be X. We don't know it yet. So we take this, and now we move on to the second isotope. Here's the mass of boron. We're going to take the mass of chlorine-37, 36.97, and multiply that by the abundance. It's 0.8 here, and for chlorine-37, it's going to be 1 minus X. So we add those two together, and unlike down here where we don't know the atomic mass, we already do know the atomic mass for chlorine. That should be 35.45. Now we've set up our equation, and all we have to do is rearrange, multiply, and divide a little bit, and we can solve for X. Let's do that. So I'm going to rewrite this, and the first thing I'm going to do is I'm going to distribute 36.97 between these parentheses. Okay, so I'm going to get 36.97 times 1 minus 36.97x equals 35.45. Now I have two x terms, this one and this one, so I'm going to do 34.97 x minus 36.97x, and that's going to give me 2.00x, negative 2.00x plus 36.97 equals 35.45. Now I want to get rid of this from this side of the equation, so I'm going to subtract 36.97 here, minus 36.97 here, and that is going to give me negative 2.00x equals negative 1.52. These are both negative, so I can multiply both sides of the equation by negative 1 to make them both positive. So I'm going to get 2.00x equals 1.52, and for the very last step to actually solve for x, I'm going to do x equals 1.52 divided by 2.0. I've just divided both sides by 2.0. I'm going to move up here, I've got a little bit more room, and now I can finally say that x equals, these divided together, equals 0.760, or Cl35, because that's what x is after all, equals 76.0%. Okay, now let's do the other part, which is chlorine-37. So that's going to be 1 minus x. It's going to turn out to be 0.240, and just multiply this by 100 to get the percent. I'm going to get chlorine-37's percentage equals 24.0%. So these are the two percentages that we were solving for. Just to review, the only really tricky thing you got to do here is set one of them equal to x and one of them to 1 minus x. And just as we saw here, that's because when you add the two percentages or decimals together, you're going to get 100%, or you're going to get 1 when expressed as decimals here. So it kind of took a while doing this problem, pausing along the way to look at how the math worked in various situations. So now let's do one more problem where we'll just go through it really fast, step by step, so you can be all ready to solve a problem like this if you see it on the homework or see it on a test. There are two naturally occurring isotopes of lithium, lithium-6 with a mass of 6.015 AMU, and lithium-7 with a mass of 7.016 AMU. What is the abundance of each? Okay, so we're going to be calculating abundance. There's one piece of information that we don't have that we need, and that is the atomic mass of lithium. How can we find it out? It's not given in the problem. We can look lithium up on the periodic table, and this number down here, 6.941, tells us the relative atomic mass for lithium. So that's the one other piece of the puzzle that we're going to need. Okay, so we got two things we're solving for here. Lithium-6, let's make the abundance of that equal to x, and lithium-7, let's make the abundance of that equal to 1 minus x. Now we'll set up an equation that works with the abundances and the atomic mass. So we'll do the weight of lithium-6, or I should say the mass of lithium-6. You know, people use them interchangeably with this stuff. It doesn't really matter. 6.015 times x plus the mass of lithium-7, 7.016 times 1 minus x. Add these together, and we should get the atomic mass of 6.941 here. Okay, rewrite this. Distribute this number here, so 7.016 minus 7.016x equals 6.941. I have my x terms here. I'm going to subtract this from this, and that is going to give me negative 1.001x plus 7.016 equals 6.941. Now to get x by itself, I'm going to subtract this from both sides of the equation. I'll get negative 1.001x equals negative 0.075. I'm going to just multiply both by negative 1, turn that positive. And for the last step, I will divide both sides by 1.001, which is not really going to do anything because it's so close to 1. It's going to be 0.075 divided by 1.001. All right, so now x over here equals 0.075. That's a decimal. To turn it to a percent, we multiply it by 100. So we're going to get 7.5%. And that is the amount of lithium-6 that we have. And then 1 minus x is going to be 0.925, or to turn that into a percentage, we multiply it by 100, and we get 92.5%. And that tells us the amount of lithium-7 that we have. So once again, the only really tricky thing is we had to set one of these isotopes equal to x, and the other we set to 1 minus x. Then we work through the math, and you want to obviously remember to take these decimals that you get at the end and turn them into percentages by multiplying by 100.